Last week we were talking about half reactions and looking at oxidation and reduction and balancing things electronically to see what was being oxidized and what was being reduced. And we defined, whoops, come on, we defined reduction. Oxidation is loss, reduction is gain. There should be an I there. And then oxidation is loss. Gain of electrons, loss of electrons. And what I promised is that you are now going to see how this applies to physical scenarios that you use every day, from your cell phone to, if you have them, home phones that are wireless with the batteries, anything with a battery in it. That's it. All works on these general principles. Not precisely, obviously your cell phone doesn't have two little beakers and a salt bridge and electrodes, but the fundamental process is still the same. So let's take a look at that. On the left side over here, what do I have? I have like zinc sulfate in this beaker of solution, and then I have this solid zinc metal probe, or anode, in the solution. And then I have this thing labeled salt bridge that is connecting this solution to this solution. So I'm going to come back to the salt bridge in a minute, but let's talk about what's happening in this left beaker. So first of all, what do I have? I have zinc coming off. So I'm starting with zinc metal. And what am I doing? I am going to zinc 2+. So I'm starting off with solid zinc, and I'm going to Zn2+. That means I am losing electrons. I'm losing precisely 2 of them. So this thing here, this is my oxidation reaction. What does that actually physically represent? So we have kind of like this zoomed in thing here. And then again, I want to point out that we have this zinc sulfate is in the beaker itself. So remember, if I put a salt into water, what am I going to get? So this would be my solid, and this would be my liquid. The salt will dissociate and make its ionic components. So sulfate has a charge of 2+, 2-, Zn has a charge of 2+. So SO4 2-. And these guys are just kind of floating around. So there is this thing that we can define in terms of each of our elements. We're going to do that at the end of this lecture, where we look at how much energy is related to something either being oxidized or reduced. And when we think in terms of that, that means that if there is an energy difference, then there are things that are more likely to be reduced and things that are more likely to be oxidized based on that energy difference. What turns out when we look at this, that zinc likes to be oxidized. It's likes is the wrong word. It's more energetically favorable for it to be oxidized. How about that? And what does that mean? That means that when these sulfate ions wander near this solid zinc anode, I get these little sulfate ions with their negativity, and they get near the metal. Well, these little surface zinc solid components then are attracted to that electronegative difference. That's kind of the wrong word. They're attracted to that amount of negative charge, so it's an electrostatic kind of attraction going on there. So it gets encouraged to leave, and then off pops from my anode my Zn2+. That's now going to happily float around with my SO4 2-. Now keep in mind, these two things are still staying separate, but it is this electrostatic attraction that encourages the zinc to jump off the metal and then become its little ionic state. And here you can see this kind of blown up image of it. So what's happening, as my zinc pops off, all of its electrons are like going back into the metal. when they go back into the metal, they're repulsed by each other. All the electrons that live within that metal find a state such that they can distribute themselves and maximize attraction and minimize repulsion. So if I have a piece that is electrostatically neutral, there's only so much kind of polarizability within that metal before I get motion of electrons. If the electrons have nowhere to go, this thing doesn't happen, because I'm going to have more repulsiveness happening in my anode than I have attractiveness going on. So I have to have a couple of things to happen here. I have to have a path. Here's my path for those electrons to take. So as I'm building up the repulsion of all those little negative guys inside of my metal, they can flee. So I get this like chain reaction of electrons in motion. So I have to have that. And the other thing I have to have is, in this solution, coming back to the salt bridge now, I have to have an ability to maintain neutrality. So if you put your finger into the solution, or this zinc sulfate solution, you're not getting zapped by it. So it's not going to have an overall charge. What the salt bridge does is help balance out this kind of loss and gain of cations and anions. So in this case, I'm generating zinc 2+, and I'm going to get a little bit more of my sulfate ions coming into that solution to balance out the zinc 2+ that's now been released. And so it has, you can see these kind of like little looking plugs here. And think of that kind of as a filter that kind of holds our charges and allows, it's a membrane that allows an exchange of those cations and anions. And it's all of this kind of attraction repulsion being built up there. So without that, I would end up building up something that is overall charged. Well, life just doesn't like doing that. So we have to give it away to balance. Otherwise, we're going to short out our circuit. It's just not going to work. So the salt bridge has to have the anion and cation of the solution, or a similar cation. So it doesn't have to be precisely the ions that are in our solution. We're going to get to the other side here in a second, to help maintain that neutrality. So now my electrons flow up, and there's this thing called a voltmeter. What is the voltmeter reading? It's reading a potential difference between this solution and this solution. It's kind of interesting how it happens, but in the physics world, we define that in terms of Ohm's law, which this is only for info only. You're never going to do anything with this other than just me explain it. And anyhow, so it builds up this potential difference between the two. So one that is wanting to give up electrons and another that is willing to accept it. If I have a potential difference between those, so some place for them to go, then I get electron flow. Electron flow is this thing called current. So everything has this natural resistance. I'm not going to go into that at all. Just that materials, by the way they're set up, some things allow for an easier flow of electrons, and some things are more resistive to that flow. So when I have the ability for those electrons to move, I have the ability to generate current, and then I have just this natural resistance, or a resistor that's actually thrown into the circuit to make it all work. And what the voltmeter is reading is that potential difference, the flow and then the overall resistance, and it gives us a handy-dandy little number. Well, this handy-dandy little number, that's something like, if you grab a 5-volt battery, that's what you're reading, is this difference between the two cells and the ability for the current to flow through those two cells. So let's come on over here then. I have what's happening here. Oh, let's talk about what's happening to this guy over time. So if I have solid zinc turning into zinc ions, this thing over time, actually I'll do it down here. Let's erase this. What's this going to look like over time? It's going to get smaller and smaller and smaller. In fact, what you'll start to see is like this kind of sad looking little broken up piece of zinc. That's because the solid has gone off into solution. So my zinc is getting smaller. Getting smaller. So what's happening on the right side is the opposite. My electrons are going to come in. Let's see, and you can see here I am gaining electrons. So I have these copper ions floating around in the solution, and all of a sudden these electrons come in and start filling up this bar. What is more energetically favorable to copper is, instead of being attracted to these sulfate ions and jumping off into the solution, it is more energetically favorable for it to suck, if you will, copper ions out of the solution. So I'm going to start building up. So here's my copper. You can see this. Actually, we'll do it right here. What's going to happen over time is my little electrode is going to get bigger and bigger and bigger. So there is a limiting factor here, right? If I use up my entire anode, or my cathode is like so bizarrely shaped that it can no longer accept any more solid. So in other words, there's no ability to reproduce any kind of the characteristics that go with our solids, then everything comes to a stop. Because remember, I need to balance out that attraction repulsion. So if I don't have anything else to kick off into solution on the zinc side, then it's coming to a halt. And if I have no ability to accept electrons and make more of my solid, everything's going to come to a halt. So these things do have a limited lifespan, and they are reversible, which is really cool. And we'll talk about how you can do that. So let's see what else. So I come here, and you can see that my electrons are building at the surface. And what are these? These are little copper ions being attracted to and making it this kind of bulkier thing over time. So that is our voltaic cell. And let's go ahead and label this